Let's get straight to the point. Imagine we have a function r over h times x. Next, imagine some little rectangle with base dx. Now, if we move to the third dimension and rotate our function around the axis such that we make one full revolution, our function draws some solid, in this case a cone, and our little rectangle draws a disk or radius f of x and thickness dx. Now, if we integrate all of those disks, we are going to get the volume of the solid that's called the method of disks. The volume of one disk is going to be pi y squared times his thickness dx. Next, we replace y with the function. Now, the total volume of the cone is going to be the integral from 0 to the height of the cone of the volume of every little disk. Let's move with another method. Imagine we have a circle that intersects a cylinder at the circumference and makes an angle of 45 degrees with the base of the cylinder. We are trying to find the volume under the circle. For that, we see that the cross-sectional area is a triangle. Now let's focus on the base of the cylinder. We are trying to find the base of our triangular cross-section as a function of y. Now the base of the cylinder is b, and by basic trigonometry we found his base. And because the angle is 45 degrees, the height is the same. Now the volume of our triangle is 1/2 the base times the height times his thickness. dy, multiplying, we lose the root. Then if we integrate all of those triangles, we have found the total volume under the circle. Let's move with another method. Imagine we rotate two functions with the x-axis. A tiny rectangle will generate a solid with the shape of a washer with thickness dx. That's what we call the washer method. Now let's call our upper function f of x and our lower function g of x. A washer is formed because our tiny rectangle lives only between those two functions. Hence, the rectangle will encompass less area. Taking the whole of the two functions, a solid is formed. Now, the volume of a single washer is pi times the upper radius minus the lower radius times the thickness dx. Now, if we integrate the volume of all of those washers, we will get the total volume of the solid. Now, let's move to another method. Imagine we have a function called f of x and some tiny rectangle with base dx. Now this time we rotate our function around the y-axis. Doing a complete revolution, we see that our tiny rectangle now generates a cylindrical shell with height f of x and radius x. Now if we stretch the cylindrical shell, we see that a rectangle with base 2 pi x and height y is formed. Now if we integrate every shell, we get the total volume of our solid that's like the inverse operation of peeling an onion. That's what we call the method of cylindrical shells. Now, the volume of one of those cylindrical shells is the base 2 pi x times the height, y times the thickness dx. Now, the total volume of our solid is going to be the integral of all of those tiny cylindrical shells.